Hi guys, welcome back to the Boolean Logic series. My name is James here. You can just call me Jimmy. And today we're going to be covering logic gates. So the first gate that I want to cover in the logic gate is the AND. So AND looks something like this. And I'm going to draw an AND just to be extra clear in this. So the AND is a circuit, and this is going to have a complementary table to it. So let's count up in binary on this side of the table. So 0, 0, 0, 1, 1, 0, 1, 1. So we counted up to binary on this side. So the AND gate, its sole purpose is if there is a 1 and a 1, it produces a 1. And if there's anything else, if there's, let's say, a 1 and, I don't know, a 0, and this is going to be equal to 0. So essentially the AND gate, it detects if there's both 1s on this side, and if there isn't both 1s on this side, then it creates a 0. So we could create a table out of this. And this table shows what happens when you put which inputs which. So the 0 and the 0 for the AND gate, put this here, and the 0 and the 0, well, we already know that the 1 and the 1 create the 1. So 0 and 0 not equal to 1 and 1. 0, 0, 1 not equal to 1, 1, 0. 1 and 0 not equal to 1, 1, 0. 1 and 1, well, that's what we're looking for, so it's a 1. And that's what an AND gate is. So I'm going to move this down here. Oops, look at that little N. Alright, so we know what an AND gate is now, but what is the NAND gate? And the NAND gate is like the evil twin of the AND gate. So we're going to draw it down here. You can tell it's the NAND gate by this little circle here. And you're going to see this a lot, because each gate has its complementary gate that's opposite of it. So NAND, I'm going to draw it right here, NAND is a gate that takes a 1 only if there's a 0 and a 0. And it functions exactly opposite of an AND gate. So we're going to draw the table here, and we're going to count up in binary on this side like we always do. Now 0 and 0, that's exactly what we're looking for. That's a 1. 0 and 1 not equal to 0 and 0. 1 and 0 not equal to 0 and 0. 1 and 1 not equal to 0 and 0. So we could see, if we take a look at these gates right here, these gates, the AND gate and the NAND gate are different. This is the OR gate, and it looks like the AND gate, except it's a little curvy in the back. So this is the OR gate symbol, and I'm just going to draw OR here. Now, the OR gate works sort of like, it's pretty different from the AND gate. So essentially, if there's a 1 at any point, oops, drew that wrong, we're counting up in binary. So if there's a 1 at any point in this pairing, then the output's going to be 1. So 0 and 0 create 0, 0 and 1 create 1, 1 and 0 create 1, 1 and 1 create 1. And think of it as, if we see a 1, then the 1 just goes over here. But in this one, there's no 1 to carry over, because they're both zeros. So it's just going to carry over 0. But let's see this in action. Now, using this truth table, we're going to zoom in on this OR gate. So let's say that we have something that's powered on and something that's powered off. An electrical signal, no electrical signal. And we run that through an OR gate. Well, let's look at our truth table. Now, the 1 always wins against the 0. So think of it, the 1 is just going to carry over here. Boom, that's our OR gate. Now, what OR gate combination creates 0? Well, we could just write 0 and 0. The combination would be 0 because there's no 1 to carry over. There's just zeros, so simple as that. Now, you're going to learn that each pair has its complementary anti-pair. It's like yin and yang. So I'm going to move this over here. We're going to zoom in on this. But the NOR gate, which is like the NAND gate, but for OR, it's spelled N-O-R, is the exact opposite of the OR gate. Just like the NAND gate is the exact opposite of the AND gate. So, let's draw this truth table again, but the exact opposite. So, we're just going to take the outputs and we're going to draw their opposite. So 0, opposite 0 is 1, opposite 1 is 0, opposite 1 is 0, opposite 1 is 0. And we're going to count up in binary on this side. And the NOR gate, it's the opposite of the OR gate. So if we see a 1, or if we see a 0, then we're going to carry over that 0 to the input. So let's try this out. So I'm going to bring this down here. Oops, let me get rid of that. Alright, so let's say that we have 1 and 1 in the circuit. What do you think is going to happen? Well, there's literally no 0 to carry over. So it's just going to be 0 in this case. However, if we do have a 0 that carries over, then it's going to be a 1. So 0 and 1. Let's put that in the input. Now, there's a 0 to carry over. So the NOR gate is essentially saying, is there a 0 in this gate? If there is, then the 0, it becomes a 1. And it's essentially checking if there's both 1s in the circuit. So if there's a 1 and a 1 in the NOR gate, then the NOR gate is going to return 0, since the NOR gate is not like two 1s. So now we've covered that the NOR gate is opposite of the OR gate. And that means that if we input, this has similar properties to the AND gate. So if we put both, let me get rid of that, a 1 into 1, we're going to get 0. And this, of course, is going to be the exact opposite of the NOR gate, which when we put a 1, sorry, I made a mistake here. 1 and 1 create 1. And this is going to be the exact opposite of the NOR gate, where the 1 and the 1 create the 0. So now we know how the NOR and the OR gate work. The XOR gate, this is a little bit of a funky one. But the XOR gate could be represented with a little bump in the back. But it's pretty similar to an OR gate. So we're going to draw this here, XOR. So what the XOR gate does, and this is my favorite gate, but it sees if the outputs are different, or if the inputs are different. So it's going to check, is 0 and 1 different from each other? And if they are, then return a 1. Now what this means is, if there was, say, a 0 and a 0, then these are not different from each other. So this is going to return me, as it should, a 0. And if we have a 1 and a 1 over here, well, we know that the 1 and the 1 are not different. They're the same. It's just going to return a 0. So essentially asks, are the outputs the same? And let's see this in action. So we're going to take a look at its truth table over here. So we can count up in binary. So 0 and 0. Now 0 and 0 are the same, so it's going to return me 0. 0 and 1. These are actually different, so I'm going to get a 1 over here. 1 and 0, those are different, so this is going to give me 1. 1 and 1, these are not different. These are the same input, so I'm going to get a 0. And that is the XOR gate. Now, for every gate, there's an opposite gate. It's like yin and yang. So we're going to have our XOR gate. And we're going to draw it over here, but with a little circle. So the XOR gate. So what the XOR gate does, I'm going to move this over here, is the XOR gate does the exact opposite of the XOR gate. So if I put a 0 and 0 over here, now these are the same, and if they're the same, that's going to return me 1. So essentially the XOR gate says, if two inputs are the same, then give me a 1. So let's take a look at this in action. Counting up in binary, we have the drill. Now 0 and 0 are the same thing, so we're going to get a 1. 0 and 1 are not the same thing, so we're going to get a 0. 1 and 0 are not the same thing, we're going to get a 0. 1 and 1 are the same thing, we're going to get 1. So let's compare these inputs side by side. XOR. And we do come to the conclusion, again, that I'm going to move these side by side for you. We come to the conclusion, again, that the inputs or the outputs of each side are opposite of each other. So 0 and 1 are opposite, 1 and 0 are opposite, 1 and 0 are opposite, 0 and 1 are opposite. And as I said, this is by intention, because the XOR and the XNOR are the opposite of each other. Chances are, if you see an N in the name, then these gates are the opposite. So now we're going to do one more gate. I'm sorry, has to be done, but this is actually a pretty easy one. So this gate doesn't really take two inputs and compare them. This is the NOT gate, and it only needs one input to function. And essentially what the NOT gate does is if it sees a digit, it's going to return its opposite. So 1 turns into 0. And this is pretty simple. We're just going to do it again. If we put a 0 in here, it's going to turn into a 1. This is essentially a number changer. So if we see a 0, we're just going to change it because we don't like 0. If we see a 1, we're going to change it because we don't like 1. So that's the NOT gate. And the name implies what it is. It just takes what it is and makes it what it's not. So just like that, we've covered all 7 gates. Now, we've learned a lot in this lecture, but let's do a few practice problems. So This is an AND gate. You don't have to know these symbols like the back of your hand yet, but I just encourage you to sort of get an idea as to how they look. With the AND gate, let's say we put a 1 and 0. What is it going to produce? Well, if you remember the AND gate, it's like a 1 detector. Or it's a 1 and 1 detector. It's in the name. So if there's a 1 and another 1, if there's two 1s, that's going to return you 1. So the question is, do you see two 1s here? You don't? Well, this is just going to be 0. Now we're going to try this with a different question. So now we're going to do XOR. This isn't drawn the best. So let's say we put 0 and 1. What is our output going to be? I'll give you some time to work this out. Well, an XOR gate essentially measures if the outputs are different. If the 0 and the 1 are different, then give me a 1. So it's essentially 0, it's a difference checker. Now, the XOR does not like two of the same input. It likes two different inputs. It likes to get both flavors. That makes sense. So now let's do a few more. Let's run it with a NOR gate. Now we're going to draw NOR here. So for NOR, let's say we put a 1 and a 1. What are we going to get? I'll let you solve this one. Alright, so the NOR gate. Now we know that the NOR is the opposite of the OR gate. And we know that the OR gate is a 1 detector. So we're going to count up in binary on this side. Now if we see a 1 anywhere in these inputs, then we just draw a 1. So 0 and 0, I don't see a 1. 0, I see a 1 here, see a 1 here, see a 1 here. I see two 1s over here. So we know that the NOR is just going to be the opposite. So NOR, we're just going to take the exact opposite of the input. So 0, 0, we can count up in binary on this side. And we're just going to take the opposite of each one. So 0, this becomes a 1, 1 becomes 0, 1 becomes 0, 1 becomes 0. So for the NOR gate, if you have a 1 and a 1, we can check our trusty truth table and determine that we have a 0. So that's the cool thing about binary logic, is you don't even need to know half of these gates. Because if you see that NOR, and you just remember that NOR is the opposite of OR, then we could assemble the OR truth gate, and we could take the opposite input like we just did. So now we know that 1 and 1 simply 0. Now we can do one more, and that'll be it for the day. So we're going to take this, and this is an easy one actually. Now this is the NOT gate, and let's say we put a 1 into here, what we can get out? Well, the 1, the opposite of 1 is 0. So it's as simple as that really, because the NOT, it takes an input and it returns the opposite of that input. So I hope you guys learned something today. Um, if you're sitting down at the table with your family and they ask you what you learned, say that you learned about logic gates. So I hope you enjoyed this video. Have a great day if you haven't had one already, and come back for the next episode. Goodbye.